You think you understand what it means to ask for an explanation. Someone asks a question, you give an answer. Simple. The question makes sense, the answer makes sense, everyone walks away satisfied. But what happens when the question itself is broken? What happens when the thing you're asking for doesn't exist, can never exist, and the very act of asking for it reveals a fundamental misunderstanding about how reality works? Richard Feynman faced exactly this situation in a BBC interview decades ago. The interviewer asked him a simple question: why do magnets repel? It seemed reasonable. Magnets are mysterious. They push and pull through empty space. Surely a brilliant physicist could explain why they do that. Feynman refused to answer. Not because he was being difficult, not because he didn't understand magnets. He understood them better than almost anyone alive. He refused because the question was impossible to answer in the way the interviewer wanted. And when Feynman tried to explain why the question was impossible, the interviewer got frustrated. The audience got frustrated. People watching at home thought Feynman was being evasive, arrogant, or deliberately obscure. But he wasn't. He was being honest, in a way that most scientists aren't willing to be. He was telling a truth that nobody wanted to hear. The truth is this: when you ask why magnets repel, you're not actually asking for information. You're asking for comfort. You're asking someone to connect this unfamiliar phenomenon to something you already understand. You want a story, a narrative, a chain of cause and effect that ends with something familiar, like springs or rubber bands or hands pushing against each other. You want the strange thing to become normal. And Feynman understood that he couldn't give you that. Not because he lacked the skill to explain things simply. He was legendary for making complex ideas accessible. But because what you were asking for literally does not exist. Magnetic repulsion is fundamental. There's nothing underneath it to compare it to. There's no deeper layer of reality where magnets are explained by something simpler. The chain of why has to stop somewhere. And for magnets, for all electromagnetic phenomena, it stops at the electromagnetic force itself. This creates a profound problem. Because most people, when they ask for an explanation, have a specific shape in mind for what that explanation should look like. They want you to say, magnets repel for the same reason that springs push back when you compress them. They want a mechanical analogy, something they can visualize with familiar objects doing familiar things. But the electromagnetic force isn't like a spring. It's not similar to a spring. Springs themselves work because of electromagnetic forces. You can't explain electromagnetism by comparing it to something that is electromagnetism. That's circular. That doesn't explain anything. It just pushes the mystery around. Let Feynman's approach reveal what's really happening here. When you push your hand down on a table, why doesn't it go through? Most people say because the table is solid. But what does solid mean? It's not an explanation, it's just another word for the thing you're trying to understand. Push deeper. Why don't the atoms in your hand pass through the atoms in the table? Someone might say because atoms are solid too. But that's wrong. Atoms are almost entirely empty space. If you scaled an atom up to the size of a football stadium, the nucleus would be a pea at the center, and the electrons would be tiny specks way out near the seats. Everything in between is emptiness. Your hand is essentially empty space. The table is essentially empty space. So why don't they interpenetrate? The answer is electromagnetic repulsion. The electrons in your hand have negative charge. The electrons in the table have negative charge. Like charges repel. When you push down, you're feeling countless trillions of electromagnetic interactions, each electron pushing away from every other electron with enormous force. Those forces add up to what you experience as solidity, as resistance, as the feeling of the table being hard and impenetrable. But here's what should shatter your understanding of the world. The electrons in your hand never actually touch the electrons in the table. They repel at a distance, a tiny distance measured in fractions of nanometers, but still a distance. There is always a gap. Nothing is touching. You have never touched anything in your entire life. What you call contact is electromagnetic repulsion operating across infinitesimally small distances. Now, with magnets, the gap is bigger. You can see it. You can hold two north poles near each other and watch them push apart with nothing visible between them. You can slide a piece of paper through the gap. You can see the emptiness. And that makes you uncomfortable. That feels weird. That feels like it needs an explanation. But here's the critical insight that Feynman was trying to communicate. The force pushing those magnets apart is exactly the same force that stopped your hand at the table surface. It's not similar. It's not analogous. It's identical. The electromagnetic force. The only difference is scale. The distance between the magnets is large enough that you can see the gap. The distance between your hand and the table is so small that you can't see it, so your brain interprets it as contact. But it's the same phenomenon, the same force, the same physics. The mystery you feel when magnets push through visible empty space is not a mystery in the physics. It's a mystery in your psychology. You've spent your entire life pushing on solid objects. You've built up an enormous database of experiences. Pushing, grabbing, lifting, dropping. Your neurons have wired themselves around those experiences. They've created patterns, expectations, an intuitive framework for how the world works. And because electromagnetic repulsion at atomic distances is so ubiquitous, because it happens in every single interaction you've ever had with physical objects, it feels normal. It feels obvious. It doesn't seem to need explaining. But magnets pushing at centimeter distances, that's less familiar. That's outside your everyday experience. So it feels strange. It feels wrong. It triggers your why response. But the strangeness is in your head, not in the universe. The universe is perfectly consistent. Electromagnetic forces act at all distances. From nanometers to meters, to kilometers, to light years. The force falls off with distance, according to specific mathematical laws, but it's always there, always acting, always the same force. Your discomfort is about familiarity, not about physics. This reveals something crucial about what it means to ask for an explanation. When most people say they want an explanation, they mean they want you to connect the unfamiliar to the familiar. They want you to take their existing mental framework and slot the new thing into it. They want you to preserve their intuitions. But sometimes, and this is what Feynman understood, the universe doesn't work the way your intuitions expect. Sometimes, reality is genuinely different from everyday experience. And in those cases, the honest thing to do is not to pretend there's a comfortable analogy. The honest thing is to say your intuitions are wrong, and you need to build new ones. Think about the chain of why that Feynman would trace. Why does ice float on water? Because ice is less dense than liquid water. Why is it less dense? Because the molecular structure has more space between molecules. Why does it have that structure? Because of how hydrogen bonds arrange themselves at freezing temperatures. Why do hydrogen bonds arrange that way? Because of quantum mechanical properties of electrons in water molecules. Why do electrons have those properties? Because of the equations of quantum mechanics. Schrödinger equation, the Pauli exclusion principle. Why do those equations hold? And here the chain stops. Not because physicists don't know the answer, but because there isn't a deeper answer. Those equations describe fundamental reality. They're tested against experiments. They work. They make predictions. They allow us to build technology. But they don't emerge from something more fundamental. They are the foundation. At each step in that chain, you're pushing the question back one level. You're going deeper. But eventually, you hit bedrock, and the bedrock of our understanding is a small set of fundamental forces and fundamental equations. For magnets, for all electromagnetic phenomena, that bedrock is the electromagnetic force and the equations that describe it. Maxwell's equations in classical electromagnetism, quantum electrodynamics at the quantum level. These equations are stunningly accurate. They're tested to incredible precision. The magnetic moment of an electron can be calculated and measured to 11 decimal places. And they match perfectly. That's not because the equations are convenient approximations. It's because they're describing something real, something fundamental about how the universe operates. But those equations don't explain the electromagnetic force in terms of something else. They describe it. They tell you how it behaves. They give you rules for calculating what will happen in any given situation. They provide predictive power. But they don't tell you why the force exists in some deep philosophical sense. And this is where most people get confused. They conflate description with explanation. They think that if you can describe something mathematically, you've explained it. But description and explanation are different things. Description tells you how. Explanation tells you why. And for fundamental forces, there is no why. There's only how. When Feynman said he couldn't explain why magnets repel, he didn't mean he couldn't describe the phenomenon. He could describe it in exquisite detail. He could write down the equations. He could calculate the force as a function of distance, orientation, and magnetic strength. He could predict exactly what would happen in any experimental setup. He could derive the behavior from first principles. He could connect it to the broader framework of quantum field theory. But none of that would satisfy the interviewer, because the interviewer wanted a why that ended with something from everyday experience. He wanted magnets are like springs, or magnets are like air pressure, or magnets are like interlocking gears. He wanted a mechanical analogy, and Feynman couldn't give him that because no such analogy exists. Consider what it means to really understand something in physics. It doesn't mean matching your intuition. It doesn't mean making you comfortable. It means giving you predictive power. If you truly understand magnets, you should be able to answer questions like these. How does the force between two magnets change if you double the distance between them? What happens if you heat a magnet above its Curie temperature? Why do some materials become magnetic in the presence of a magnetic field? How do you calculate the magnetic field produced by a current flowing through a wire? If you can answer those questions, if you can make accurate predictions and build working technology, then you understand magnets. That's what understanding means in physics. Not comfort, not familiar analogies. Power. The ability to predict, to calculate, to manipulate nature. And by that standard, physicists understand electromagnetism better than almost anything else. Quantum electrodynamics is the most precisely tested theory in all of science. It makes predictions about phenomena that are then measured in laboratories around the world. And the predictions match reality to absurd levels of precision. This isn't speculation or philosophy. This is verified, tested, working knowledge. When engineers design electric motors, they use electromagnetic theory. When they design generators, transformers, radio transmitters, computer chips, they're all using the same fundamental equations. And these devices work. They work so reliably that you don't even think about it. You flip a switch and the light comes on. You plug in your phone and it charges. That reliability is proof that the theory is correct, that we've captured something real about how nature operates. But notice what happened. Understanding magnets didn't come from finding a familiar analogy. It came from writing down equations, testing them against experiments, using them to make new predictions, building technology based on those predictions, and verifying that the technology works. That process took centuries. It involved brilliant people like Coulomb, Ampere, Faraday, Maxwell, and eventually Feynman himself contributing to quantum electrodynamics. They didn't succeed by making electromagnetism familiar. They succeeded by making it precise. They built mathematical structures that accurately describe what the electromagnetic force does. And that mathematical description is the understanding. This brings us to what Feynman meant when he said magnetic forces are fundamental. Fundamental doesn't mean simple. It doesn't mean easy to understand. It means bottom level. It means there's nothing underneath. Everything else gets explained in terms of fundamental forces, but fundamental forces themselves don't get explained in terms of anything else. They're the axioms of reality. You start with them and build up. You don't break them down further because there's nothing further to break them down into. The electromagnetic force is one of 4 fundamental forces in nature. The others are gravity, the strong nuclear force, and the weak nuclear force. These 4 forces are responsible for everything that happens in the physical universe. Gravity holds planets in orbit and makes things fall. The strong force holds atomic nuclei together. The weak force is responsible for certain types of radioactive decay. And the electromagnetic force, that's responsible for almost everything in your daily life. Chemistry is electromagnetic forces between electrons in different atoms. Light is oscillating electromagnetic fields. Heat is atoms vibrating, held in place by electromagnetic forces. Electricity is electromagnetic forces pushing electrons through wires. Magnetism is electromagnetic forces aligned in particular ways. All the pushes and pulls you feel, all the sensations of touch and pressure and resistance, they're electromagnetic. When you sit in a chair, electromagnetic forces between electrons prevent you from falling through. When you see colors, electromagnetic waves are hitting your retina. When your muscles contract, electromagnetic forces are driving chemical reactions in your cells. You are, in a very real sense, a walking pattern of electromagnetic interactions. Everything you experience, except for falling under gravity, is electromagnetic. And Feynman understood this. He saw that the question, why do magnets repel, was really asking, why does the electromagnetic force exist? And that question has no answer, because the electromagnetic force is fundamental. It's not caused by something else. It's not derived from something simpler. It just is. Now, you might protest. You might say, surely quantum mechanics explains electromagnetism. Surely there's a deeper theory. And yes, quantum electrodynamics gives us a quantum description of the electromagnetic force. It describes how photons mediate interactions between charged particles. It gives us Feynman diagrams, beautiful mathematical tools for calculating probabilities of different outcomes. It reveals that what we call the electromagnetic field is really a quantum field, a kind of rippling potential that permeates all of space. But notice what quantum electrodynamics does. It refines our description. It makes our calculations more accurate. It extends electromagnetic theory into regimes where classical physics breaks down. But it doesn't explain away the electromagnetic force. It doesn't reduce it to something more familiar. It just describes it at a deeper level, with more precision, in terms that are even less familiar than classical electromagnetism. Quantum field theory is deeply weird. It violates every intuition you have about how the world works. Virtual particles popping in and out of existence, wave-particle duality, probability amplitudes that interfere like waves. None of this matches everyday experience. None of it provides comfort. But it works. It makes predictions that are verified to incredible precision. And that's what matters. Not whether it matches your intuition, but whether it matches reality. Feynman himself was one of the architects of quantum electrodynamics. He developed techniques, now called Feynman diagrams, that revolutionized how physicists calculate quantum interactions. He won the Nobel Prize for this work. And yet, even with all that deep knowledge, or perhaps because of it, he understood that the chain of explanation has to stop somewhere. You can describe things at deeper and deeper levels, with more and more precision, but you never escape the fact that fundamental forces are fundamental. This is the hardest thing for people to accept. We're psychologically wired to expect that everything has a cause. Every event has a reason. Every phenomenon can be explained in terms of something prior. This intuition serves us well in everyday life. If the car won't start, there's a reason. Dead battery, out of gas, faulty starter. If the plant is wilting, there's a reason. Not enough water, too much sun, disease. We trace back causes and find explanations. But physics reveals that this causal chain has a foundation. At the bottom, there are fundamental entities, fundamental forces, fundamental laws. And those don't have causes. They're not effects of something prior. They're the starting points. The universe operates according to certain rules. We can discover those rules, test them, use them. But we can't explain why those rules exist rather than different ones. That's not a failure of science. That's the structure of reality. When Feynman refused to answer the BBC interviewer's question, he was respecting this structure. He was refusing to pretend that magnetic forces can be reduced to something more familiar. He could have given a comfortable lie. He could have said, magnets are like springs, or think of magnetic fields as rubber sheets stretched through space. Or imagine invisible ropes pulling and pushing. The interviewer would have nodded. The audience would have felt satisfied. Everyone would have walked away feeling like they understood. But they wouldn't have understood anything. They would have been given a false analogy, a story that sounds good, but doesn't actually correspond to reality. And Feynman wasn't willing to do that. He had too much respect for the truth and too much respect for the audience. Think about what Feynman was really saying. He was saying that if you want to understand magnets, you need to change what you mean by understanding. You need to let go of the idea that understanding means connecting to familiar experience. You need to accept that reality at its foundations is genuinely different from everyday life. And you need to build new intuitions, mathematical intuitions, intuitions based on working with equations and solving problems and making predictions and testing them. After months or years of working with electromagnetic theory, something shifts. The equations start to feel natural, not because they match your everyday experience, but because you've built a new kind of experience, a mathematical experience, an experience of how fields and forces behave. And then magnets aren't mysterious anymore. They're exactly what you'd expect. They're inevitable consequences of the fundamental structure of reality. But you can't shortcut that process. You can't skip straight to the intuitive understanding by hearing a 5-minute analogy. The analogy will feel good in the moment, but it won't give you real understanding. Real understanding comes from doing the work, learning the mathematics, solving problems, making predictions, testing them against reality. building up a new framework in your head. That's how physicists actually understand magnets, not through analogies to springs or ropes, but through working with Maxwell's equations, through calculating magnetic fields, through understanding how moving charges create magnetic effects, through seeing how it all connects to relativity and quantum mechanics. That process builds genuine understanding, deep, functional, predictive understanding. And here's something beautiful that emerges from this process. Even though magnetic forces are fundamental, even though they can't be reduced to something simpler, they unify an enormous range of phenomena. The same electromagnetic force that makes magnets push apart also explains why atoms hold together. It explains chemistry, why some substances react and others don't, why molecular bonds form and break. It explains how your neurons fire, electrical signals traveling through your brain. It explains light, electromagnetic waves propagating through space. It explains why the sky is blue, why metals conduct electricity, why objects have color, why radio works, why your computer functions. All of these seemingly different phenomena, all explained by the same fundamental force. That's what should blow your mind. Not that we can't reduce magnets to something simpler, but that we can reduce thousands of different phenomena to the same underlying force. That's unification. That's discovering that beneath apparent complexity, there's a deep simplicity. Simple rules, fundamental forces, generating incredible richness and variety. And the electromagnetic force is at the heart of that. It's not an isolated mystery. It's the thread that connects almost everything in your direct experience of reality. When Feynman said, "You can't explain magnetic repulsion by comparing it to something familiar," he wasn't saying magnetic forces are unknowable or mystical. He was saying they're fundamental. And fundamental forces don't need to be explained by something else, because they explain everything else. The direction of explanation goes the other way. You don't explain magnetism by reference to mechanical systems. You explain mechanical systems by reference to electromagnetism. Why do springs push back when compressed? Because electromagnetic forces between atoms resist being pushed closer together. Why do solid objects maintain their shape? Because electromagnetic forces hold atoms in particular arrangements. Why can you pour water? Because electromagnetic forces between water molecules are weak enough to allow flow, but strong enough to keep the molecules together. Everything you think of as normal, as obviously not needing explanation, that's all electromagnetic. The electromagnetic force is so pervasive, so fundamental to everything you experience, that you've stopped noticing it. You think solid objects are just naturally solid. You think touching something is simple and obvious. You don't realize that every single sensation, every push and pull and interaction, is electromagnetic forces acting at a distance. Nothing is touching. There are only fields and forces, particles pushing and pulling on each other through space. And the familiar mechanical world you think you understand, that's the thing that needs explaining. That's the phenomenon you should find mysterious. The fact that electromagnetic forces are so precisely balanced, that positive and negative charges cancel so exactly, that the net effect feels like simple, solid, mechanical contact. That's the miracle. That's what required billions of years of cosmic and biological evolution to produce. A world where electromagnetic forces are hidden behind an illusion of mechanical contact. Feynman understood all this. He saw that the interviewer was asking him to explain the real thing in terms of the illusion, to explain fundamental electromagnetic forces by comparing them to mechanical systems that are themselves electromagnetic. It was backwards. It was inside out. And he couldn't do it. He wouldn't do it. Not because he was pedantic or difficult, but because he cared about truth more than comfort. He respected the universe enough to represent it accurately, and he respected his audience enough to tell them when their question was based on a misconception. This gets at something deep about science communication. There's a constant tension between accuracy and accessibility. You want people to understand. You want to make science approachable. But if you oversimplify too much, if you replace real explanation with comforting metaphors, you're not actually communicating science. You're communicating a fantasy, a story that sounds scientific but doesn't correspond to reality. And that does a disservice to both the science and the audience. It gives people the false impression that they understand when they don't. It makes them think physics is just familiar things with new names. It hides the genuine strangeness of reality, the genuine beauty of discovering that the universe works in ways we never expected. Feynman chose accuracy. He chose to tell the truth, even when the truth was uncomfortable. And he paid a price for it. People thought he was being evasive. They thought he didn't want to explain things simply. But that's not what was happening. He was explaining things honestly. He was saying some things are fundamental and can't be explained in terms of something else. And if you want to understand those things, you need to change how you think about understanding. You need to build new intuitions from mathematics and experimentation, not from everyday analogies. This is the lesson that goes far beyond magnets. It's a lesson about the nature of knowledge, the limits of analogy, and what it means to truly understand something. Understanding isn't always about making the unfamiliar familiar. Sometimes it's about recognizing that the unfamiliar is genuinely different and building new frameworks to deal with it. Sometimes the universe surprises you. Sometimes reality operates according to principles that don't match your intuition. And when that happens, you have two choices. You can reject it, insist that there must be a simpler explanation, demand analogies that make you comfortable. Or you can accept it, lean into the strangeness, learn the mathematics, and build new intuitions that actually match how reality works. Physicists choose the second path. They've learned to be comfortable with discomfort. They work with equations that describe reality accurately, even when those equations violate everyday intuition. They build mental models based on mathematics and experimentation. And over time, through thousands of hours of problem solving and calculation, those models become intuitive. Not because they match everyday experience, but because they become a new kind of everyday experience. A physicist who has spent years working with electromagnetic field theory develops intuitions about how fields behave. They can look at a configuration of charges and magnets and immediately sense what the field will look like, how forces will act, what will happen. That's real intuition, hard-earned intuition, based on genuine understanding. But you can't transfer that intuition through a simple analogy. You can't give someone years of experience with electromagnetic theory by saying magnets are like springs. All you can do is point them in the right direction. Tell them this is fundamental. This is what the universe does. If you want to understand it, here's where to start. Study the mathematics, solve problems, make predictions, test them, build up experience. Let the strangeness become familiar through repeated exposure, not through false comparisons to things that seem familiar but actually aren't. This brings us back to that moment in the BBC interview. The interviewer asked why magnets repel. Feynman could have given him a comfortable answer. He could have said something vague about magnetic fields and left it at that. Most scientists would have. But Feynman saw an opportunity to communicate something deeper. He saw a chance to explain not just how magnets work, but how physics works, how knowledge works, what it means to understand something at a fundamental level. He tried to convey that the question itself was based on a misconception, that you can't always explain the unfamiliar by reference to the familiar, because sometimes the familiar is itself an instance of the unfamiliar. The interviewer didn't get it. The audience didn't get it. For decades afterward, people cited that interview as an example of Feynman being difficult or arrogant. But they were wrong. It was an example of Feynman being honest in a way that most people aren't prepared to hear. He was saying, the universe doesn't owe you an explanation that matches your intuition. Your intuition evolved to help you survive on the African savanna. It did not evolve to understand quantum fields or electromagnetic forces at the atomic scale. So, when physics reveals something that violates your intuition, the problem isn't with physics. The problem is with your expectation that intuition should always be a reliable guide. And this is the final, deepest lesson. The universe is under no obligation to make sense to you. It doesn't care whether you find its fundamental principles comfortable or intuitive or satisfying. It operates according to certain rules. Those rules can be discovered through careful observation and experiment. They can be described with mathematics. They can be tested and used to make predictions and build technology. But they can't always be reduced to analogies with everyday experience. Sometimes, often, the universe is genuinely strange, genuinely different from what we expected. And the appropriate response is not to demand better explanations that make us comfortable. The appropriate response is to change our expectations, to expand our conception of what's possible, to build new intuitions based on what the universe actually does, rather than what we think it should do. When you pick up two magnets and feel them push apart, you're not encountering a mystery that needs to be explained away. You're encountering one of the four fundamental forces of nature. The same force that holds your body together. The same force that makes chemistry possible. The same force that allows light to exist. The same force that your entire sensory experience of reality depends on. That's not something to reduce to a familiar analogy. That's something to marvel at. The fact that we can describe this force mathematically, that we can predict exactly how it behaves in any situation, that we can use it to build motors and generators and computers and civilization itself, that's not a failure to explain. That's triumph. That's humanity discovering the fundamental principles that govern reality and learning to work with them. Feynman understood this. He spent his life working with these fundamental principles. He developed techniques that made quantum electrodynamics calculable and practical. He showed how to visualize interactions that were previously hidden in impenetrable mathematics. He made enormous contributions to our understanding of how the electromagnetic force works at the deepest levels. And precisely because he understood it so deeply, he knew that it couldn't be reduced further. He knew that the chain of explanation stops at fundamental forces. And he was willing to say so, even when it made people uncomfortable, even when they accused him of refusing to explain. But he wasn't refusing to explain. He was explaining something more important than how magnets work. He was explaining how explanation works. He was showing that scientific understanding isn't about replacing mystery with familiar analogies. It's about replacing vague wonder with precise description. It's about going from, "I don't know why that happens," to, "I can calculate exactly what will happen in any situation, and my calculations match reality perfectly." That's understanding. Not comfort, not intuitive satisfaction, but predictive power. So when people ask, why can't we really explain magnets? The answer Feynman gave is the only honest answer possible. We can explain magnets. We can explain them in extraordinary detail. We can describe the electromagnetic force with equations that work to 11 decimal places. We can predict magnetic behavior in any configuration. We can engineer devices that manipulate magnetic fields with incredible precision. But we can't explain magnetic forces in terms of something more fundamental, because there isn't anything more fundamental. The electromagnetic force is bedrock. It's one of the foundation stones of reality. Everything else gets explained in terms of it. It doesn't get explained in terms of anything else. And that's not a limitation. That's the structure of knowledge. Every chain of reasoning has to start somewhere. Every explanation rests on axioms, on fundamental principles that are taken as given. In physics, those fundamental principles are the fundamental forces and the equations that describe them. You can test those principles against reality. You can verify that they work. You can use them to build technology. But you can't derive them from something simpler, because they are the simplest, the most fundamental level we've been able to reach. Maybe someday we'll discover something deeper. Maybe we'll find that the four fundamental forces are actually aspects of one unified force. Physicists have been working on this for decades. But even if we succeed, even if we unify everything, we'll still hit bedrock eventually. We'll still reach a point where we have fundamental principles that can't be reduced further. That's not a flaw in our understanding. That's the nature of understanding itself. Feynman's refusal to explain magnets in comfortable terms wasn't arrogance or evasion. It was intellectual honesty. It was respect for truth over comfort. It was a teaching moment about the nature of science and the structure of reality. And the fact that so many people missed that, the fact that they saw it as failure to explain rather than explanation of a different kind, that tells us something about what we expect from science. We want it to make us comfortable. We want it to confirm our intuitions. We want the universe to be fundamentally similar to our everyday experience, just with fancier names. But the universe doesn't care what we want. And science, real science, honest science, tells us what the universe is actually like. Not what we wish it were like, not what would make us comfortable, what it is. And what it is, at the fundamental level, is strange and beautiful, and governed by principles that took centuries to discover, and that still surprise us when we really think about them. Electromagnetic forces acting at a distance. Time and space bending near massive objects. Particles existing in superpositions of states until measured. None of this matches everyday intuition. All of it matches reality. The choice is whether to reject reality because it's strange, or to embrace reality and build new intuitions. Feynman made his choice. He embraced the strangeness. He worked with it, calculated with it, understood it so deeply that it became second nature. And then, when asked to explain it in comfortable terms, he told the truth. Some things can't be made comfortable. Some things are genuinely different from everyday experience. And if you want to understand them, you need to meet them on their own terms. That's the real lesson about magnets. It's not about magnetic fields or electron spins or quantum mechanics. It's about honesty, about being willing to say, I can describe this precisely, I can predict it accurately, I can use it to build technology, but I can't reduce it to something you already understand, because it is the thing that everything else reduces to. That's what fundamental means. And once you accept that, once you stop demanding impossible analogies and start engaging with reality as it actually is, everything becomes clearer. Not simpler, not more comfortable, but clearer, more accurate, more true.